Hey folks, this is a video for a little bit of help if you need it on the Chapter 4 skills practice, because we're about to do some graphing using calculus, which has been our whole goal this unit. But you have to be good at a bunch of old stuff from algebra, which I know is not everyone's strong suit. So we'll go over some of these old things. I'm not going to do these for you, that's your job. I'll do a couple like them though. So for the section of find x-intercepts, you basically need to know what to do. Anytime you're asked to find x-intercepts, you want to find out when y equals 0. It's easier said than done, though. On some problems, it's really easy. Like, you'd set this one equal to 0 and either factor it or quadratic formula. But on a fraction, I'll show you one like that real quick. Alright, so once again, the thing you need to remember if you're ever asked to find x-intercepts is set y equal to 0. You just got to have that in your head. That's been the case no matter what math class you've been taking since algebra, really. Alright, so here's the weird one, because I know you can factor a quadratic formula, but if you get a fraction and you set it equal to 0, a lot of people do some weird stuff. So let's take a second, use your brain, and think about it. Okay, so when is a fraction equal to 0? Think about your fractions. If you had 0 on top and bottom, it actually doesn't work. We've run into that a few times with limits, but remember 0 divided by anything equals 0. So as long as the top is equal to 0, the whole equation's equal to 0. So if you ever see one of these and you're finding the x-intercepts, you don't really care about the bottom. You care about just when does the top equal 0. That makes it a whole lot easier to solve. So it's kind of like a win-win. So 4x equals negative 20, and divide both sides by 4, negative 5. So your x-intercept at negative 5, 0. Okay, so that's how you can do one of those problems there. Wanted to show you the weird one. Now if you're finding y-intercepts, well, you can probably figure it out. If you find x-intercepts by setting y equal to 0, you find y-intercepts by setting x equal to 0. So we can do the same exact problem above, and if I want to find out that guy's y-intercept, I just got to set all the x's to 0. So I'm going to go ahead and say 4 times 0 plus 20 over 0 squared minus 3 times 0 minus 10. So it's taking my original equation and putting zeros in for all the x's. Basically, this goes away, this goes away, this goes away. And you're left with 20 over negative 10, also known as negative 2, which tells me there's a y-intercept at 0, negative 2. That's going to be helpful when we're using our calculus to graph, because a couple special types of points are x-intercepts and y-intercepts. Then we can get some dots to actually draw through. So those are kind of the first two things here, right? The next thing is more new. This is how do you find where my graph is going up and going down, and this is where you find your graph is curved up or curved down. So here we got to start making tables and finding derivatives and stuff. So let's pause and come up with a good example problem. Okay, so for this next skill of finding when a graph is going up or going down using calculus, what we have to do is split your interval at the critical numbers. And if you've forgotten, critical numbers are where the first derivative is 0 or undefined. If you don't have any fractions or radicals, you don't have to worry about the undefined part. So basically, when you look at this graph, you need to know its first derivative. So first derivative is 6x squared minus 6x. Then I need to find the critical numbers. And critical numbers are when that thing equals 0. So hopefully you can see that you can factor out a 6x. And you get two answers of x equals 0 or x equals 1. So basically, that tells me my graph is going to split up at those two numbers. That's where it'll change from increasing to decreasing if it's going to. So I make a table, and I make intervals from negative infinity to 0, from 0 to 1, because I want my two answers in the numerical order. These tables get big if you have more than two. You could have 3 or 4. From 0 to 1, and from 1 to infinity. You could have a lot of these weird places. Okay, so those are the only places that the first derivative is 0. So those are the only places my graph can switch from increasing to decreasing. So on this, I want to test certain points. I can pick any point on this interval. So how about -1 for x? Because it's the smallest one. Here it's going to get irritating. You have to pick a decimal because between 0 and 1 there's not any whole numbers, so I pick that. And here I'm going to pick the smallest number I can, just to make life easier on myself. So now we're going to plug those numbers into the first derivative. Make sure you don't plug it accidentally into here. You're plugging it into here. And you only care if your answer is going to be positive or negative. You don't really care. You don't care about what number it is. So if I plug a 1 in here, -1. -1 squared is 1, so that's 6. Plus 6 is positive 12, but I really just care that it's positive. Right? If I put a 0.5 in, you get 0.5 squared is a quarter, and 1/4 times 6 minus 6 times a half, so you're going to get a negative for the whole section. Didn't really matter what number I picked on that interval. The last one, you're going to plug a 2 in. 2 squared is 4, so we got 24 minus 12, so it's positive. Alright, so what's that mean as far as increasing or decreasing? Well, if your graph is positive on the first derivative, your graph is increasing on that whole chunk. Here it's decreasing, and here it's increasing. So I'd say increasing on, we go -infinity to 0, and then use this union symbol. Kind of like means along with, and then 1 to infinity, which means the only way it's decreasing is from 0 to 1. Alright, so that's a skill you need to remember. We're going to take that up a little bit on the next question, which is finding intervals when you're concave up and concave down. It's very similar, except you're doing the same thing but with the second derivative. Okay, so I'll get let's do the same equation. So same equation, but I want the second derivative now. And if this is my first derivative, the second derivative is going to be 12x minus 6. Okay, so on this one, the only time I switch from from concave up to concave down is where the second derivative is 0. Usually we do this step kind of as just another line on this graph, but we'd have to split it 0, 1, and anytime the second derivative is 0. So, and for those of you with a good memory, you'll remember what it means when your second derivative is 0. What special point is that? The special point is an inflection point. If you can find when your second derivative is 0, you found an inflection point. So we can make a similar table, but this one only has to split at x equals 1/2. So I can go from -infinity to 1/2 and from 1/2 to infinity. And this time we're going to pick test points anywhere on there. So how about 0? Right? Pick the easiest number it is for you to work with. And I'm going to pick a 1. And remember, I'm plugging them into the second derivative, and I care is it positive or negative, because then I can tell if it's concave up or concave Okay, so second derivative, if I put a 0 in there, I get a -6, or I only care that it's negative. That's concave down. And then over here, I have a 1. I plug a 1 in here. 12 minus 6 is +6, but I only care about the positive, so it's concave up. And then I can kind of do the same kind of answer, concave up from this interval, concave down from this interval. That's similar to how you could do number 6. Okay, but you gotta go through and do it yourself. All right. Okay, let's take a look at this one. Let me pause and write a good problem here. Find critical numbers here, find inflection points. All right, so here's an example on finding critical numbers, which we already talked about before. It's where your first derivative is 0 or undefined. That's where maxes and mins can occur. Usually we care about the 0 part because the undefined oftentimes ends up as asymptotes, but we'll find it anyway. All right, so first of all, we need to find the first derivative. So f prime of x equals, and you go low, remember low d high. So low d high, which is 2x minus 2, minus high d low, the derivative of low is 1, all over low. That's kind of our deal there. And so then we're going to go maybe make this a little cleaner. So I'll take a minute and clean this up so I don't waste the time here. Just pause it. All right, so I went ahead and distributed those, distributed the negative sign, canceled stuff, combined like terms, and I got x squared plus 6x plus 2 over x plus 3 squared. Now I want to find out when is this 0 and was not undefined. Remember on the other page we said a fraction is 0 when the top is 0, and a fraction is undefined when the bottom is 0, because you're not allowed to divide by 0. So those are kind of two old rules. So f prime of x equals 0 when x squared plus 6x plus 2 equals 0. Now that's a quadratic formula kind of problem. And just to save time, you could do the opposite of b, all that stuff, or I just went in here and did it. And I got these two answers of negative 0.35 and negative 5.65. So okay, so there's two critical numbers. But I also want to find out not just when is the derivative 0, but when is the derivative undefined. And that would be when the bottom equals 0. So this guy goes to 0, and you set this one to 0 for undefined, which is a lot easier to solve because you can square root both sides. Square root of 0 is still 0, and then you move that over, and you say, okay, it's undefined at 3. So there could be a max or min here, here, or here. I'd have to use the second derivative test to check. But that's a quick recap of fractions and how you got the top to 0 for this part and the bottom to 0 for that part. Sometimes you get some ugly numbers, and I have to do quadratic formula. All right, now on to the last idea. And this idea we already kind of did, so good news there. We're going to just inflection points are where the second derivative equals 0. So you have to take the derivative of that, and then set equals 0 and solve. And you can find it. No big deal. But the difference here is you'd actually, it doesn't just want you to find what x values. You'd have to plug the x's back into the original equation to find the y values that went with them to find the point. I'm going to say skip this end behavior one because the next 2 days we're going to go over these. We'll come back to them. And I hope you can find Waldo. It's just a fun one for you. If you missed that, just quit. All right, people. I will talk to you later and hopefully see you soon. Adios.